Hello students, I welcome you all to this JEE classes. A very good afternoon to all of you. Okay, yeah. So today the topic of our discussion is inverse trigonometric functions, which is our module 19th. So I'll just wait 1 or 2 minutes so that students can join with us, right? Today we are discussing a new topic, that is inverse trigonometric function. Basically, this was from grade 12th, right? Mostly the topics of grade 11th are done, mostly, not all. So this one is from grade 12th, right? And basically we are covering the JEE portion, so we need not to take care that whether we are covering from grade 11th and 12th, all the topics has to be covered for JEE mains, right? So I welcome you all to this session. Hello Rupesh, good afternoon. Okay, yeah, Kalki. Okay. So welcome to the session. I'm your mathematics mentor for this particular channel, right? My name is Ashwita Vasan. I welcome you all to this session. So before going further, let me just tell you about Practically. Practically is an e-learning platform where you get like courses related to mathematics and sciences from grade 6th till grade 12th. So whomsoever you know, and if you haven't enrolled yourself with us at our Practically application, so I suggest you to do download the application from your Play Store, and there you will get list of all the courses which we are providing over here. Some courses are free, some are paid. Right now JEE courses for chemistry as well as mathematics are running, and some neat courses are also running. Even we are having our Python course soon at this channel, right? So whomsoever you know who has interest in all these subjects, do share this link with them. Okay, let's just start our topic for today. So basically the topics which we're gonna cover today is the introduction part, what exactly this inverse trigonometric functions are. Next main topic, these are the two main topics which we have in this inverse trigonometric function. These are principal values and graphs. What are the principal values, domain and range, everything will be discussed. After that we will plot the graph of all the inverse functions we have. Next is properties of inverse trigonometric function. This topic seems like it's quite small, but it is the most important topic if you want to cover the inverse trigonometric function, because you need to remember each and every property, right? I know that it is difficult for some students to remember the properties and how to use them. So we will be discussing each and every property as and a memory tip that how we can remember those properties in examination, right? So stay tuned with here and see the complete session so that you can remember all the properties over here, right? Let's just begin with our principal properties and graphs. We will do the introduction part on this only. So here's the introduction part, like what exactly are these inverse functions. Like if we write sine inverse, cos inverse x, tan inverse x, these are just the real numbers, or they just denote some angles. Take what exactly angles they show, such that if you take sine of this number, and you take cosine of this number, you take tan of this number, then you get x back, provided there are some conditions. These conditions mainly arise so that your inverse function is defined, right? You know that for an inverse function to be defined, the function must be 1 1 and onto right? We have already discussed this thing, that for an inverse function to be defined, it must be 1 1 and onto, and for that thing to be implemented and then we can take inverse, there are some conditions which we will study, right? What are those conditions, and because of those conditions, what constraints do we have, right? Next, we can even write sine inverse, cos inverse and tan inverse, all such inverse trigonometric function as arc sine inverse, arc cos inverse, arc tan inverse. So if so ever you see that arc sine inverse, so arc sine x, arc cos x, arc tan x in examination, this is same as sine inverse x, cos inverse x and tan inverse x. Okay, so wherever you see arc sine x or cos x or tan x, these are same as inverse trigonometric functions, right? Let's just discuss what are the domains and range if we want to say that inverse trigonometric function exists. So we have some constraints over the domain and ranges. Let's just discuss all those. We have functions and domain and ranges listed over here, right? If we have sine inverse x, so sine inverse x has its domain from -1 to 1. Why from -1 to 1? We can see this from the graph of sine x. How? Let's just see. If we draw the graph of sine x, basically you will be having graph like this, like you have these as your sine waves, right? So you know this, that if you draw a line parallel to x-axis and it cuts the graph at 2 points, then it is a many one function, and we want the function to be 1 1, so that inverse function is defined. That means if you take this part with you, you can't take this part with you, right? Because it will make like you can then make a line which is parallel to x-axis and it cuts the sine x graph at 2 points. That means you need to cut the portion after this point. Next, if you are taking only this part, then your complete function is not onto. You can take this part also, right? So that means this much portion you require only. And in all the functions, like there are more than one possibility, right? If you have sine x graph, I'll plot it again over here, right? You have this much graph with you as of now. It might be possible that some person says that you can take even this much graph also, and there is also possibility that you take this much graph also, right? So there are more than one possibilities that how much portion we take and which portion we take. So for that a basic thing which has been set and predefined to us is that we need to take first quadrant in all the in all the ranges. Like first quadrant is necessary to be written in all the ranges. After that, you need to see that whether you take second quadrant or you need to take fourth quadrant. First quadrant must be there, right? Next, based on that, you have domain of sine inverse as -1 to 1 and range will be -π/2 to +π/2, right? Next, cos inverse x, you have again -1 to +1 and y ranges from 0 to pi, 0 as well as pi included. You can remember such functions as here, like you have, if you take fourth quadrant and the fourth quadrant and first quadrant, in both the quadrants cos x is positive, cos theta is basically positive. That means you will not have any of the negative value with you. That means the function will not be onto. So for that you will be taking first and second quadrant, right? Similarly, for tan inverse x, you will firstly prefer the fourth quadrant, first and fourth quadrant. If you see that in first and fourth quadrant, you are getting all the possible values, positive as well as negative, then you will consider only the first and fourth quadrant. If you are getting only the positive values in the first and fourth quadrant, then you go for first and second quadrant, right? Like here for tan inverse x, you have minus pi by 2 to plus pi by 2, and for cot inverse x you have 0 to pi. For cosecant inverse x, you get only values varying from minus infinity to minus 1 and 1 to infinity in its domain. Like you can only give the value over here, provide the value over here such that absolute value of x, this can also be rewritten as absolute value of x is greater than equal to 1. Similarly, this condition is also same, absolute value of x is greater than equal to 1. You can see the domain of these two are same, domain of these two are same, domain of these two are also same, right? So cosecant inverse x has its domain as absolute value of x greater than equal to 1, and its range is from minus pi by 2 to plus pi by 2, where y can't be equal to 0. Right, and for secant inverse x, you have your range as from 0 to pi, and y is not equals to pi by 2. You can see that here you have for sine inverse x, tan inverse x and cosecant inverse x, you have your range in between minus pi by 2 to plus pi by 2. See, they are similar, and rest three are similar. These three are similar. So remember them as 3 and 3 triplets kind of thing, because some properties are also there which are similar for sine inverse, tan inverse and cosecant inverse x, right? The properties for sine inverse x, tan inverse x and cosecant inverse x are somewhat similar, and some properties for cos inverse, cot inverse and secant inverse x, these are also similar. So remember these triplets also, and in this form you can even remember the range easily if you remember the three triplets. Okay, so some notes which you need to take care is the first quadrant is common in all the inverse functions. This is the basic thing which we need to remember, and based on this only we decide the domain and range, right? And third quadrant is never used in the inverse function. We either use first and second quadrant, or we use first and fourth quadrant. Okay, any confusion till now? You can let me know if you have any confusion. Anyone having any confusion in this? Okay, we will move forward. Next, we have graphs of all circular function. We will draw the graph of, like, basically we will see how we can draw the graph of each function, and we will discuss the properties related to each function which you need to remember, right? So as to solve the questions, you need to remember all these basic things which we will be discussing with each graph. Okay, so the first graph over here is sine inverse x. We have domain of sine inverse x from minus 1 to 1. You can put any value for x. That means absolute value of x is less than equal to 1, right? And its domain, like range, is from minus pi by 2 to plus pi by 2, and its graph is something like this if you plot, right, as you can see over here. So what are the major points which we need to remember when we have sine inverse x are here? Some major highlights which we need to remember is sine inverse x function is always bounded by minus pi by 2 to pi by 2. You have its value ranging in between minus pi by 2 till plus pi by 2. You can't have its value as pi or 3 pi or 4 pi, any value greater than pi by 2 or any value lesser than minus pi by 2, as its range is not possible. This is the first point which we need to remember for sine inverse x. Next is sine inverse x is an odd function. This is an odd function. the property goes something like for sin x or for any of the trigonometric function, inverse properties goes similar to it, right? So if it is an odd function, that means it is symmetric about origin, right? If it would have been an even function, it would symmetric about the y-axis, but right now it is an odd function, so it is symmetric about origin. Okay. Next highlight is sine inverse x is increasing function in its domain. You can see from the graph it is always and always increasing, right? As you are increasing for x, its value for y is also increasing, right? So next property you have over here is maximum value of sine inverse x is equals to pi by 2, which occurs at x is equals to 1, right? You can see it's as it is an increasing function, right? So its maximum value will occur at the rightmost point, right? If a graph is increasing, its maximum value always occur at its rightmost point, so its rightmost point is 1. So its maximum value occurs at 1 and it is pi by 2. So its maximum value is pi by 2. Next comes its minimum value. If a graph is increasing, definitely its minimum value will be at the leftmost point. Its leftmost point is -1. So at -1 it is having the value as minus of pi by 2, right? Next is sine inverse x is an aperiodic function. Aperiodic function means it does not have any period, right? Most of the functions like here you would be getting as a periodic function because there is a basic constraint for a periodic function, that for a periodic function domain is complete R, and here you are not having the complete R as your domain. You have a concise domain over here. That means if you would have been confused with periodic, like whether it is periodic or not, if you are not able to recall what exactly is the graph, you can even recall the property of periodic function, that a periodic function is defined on the complete R, and here the domain is not the complete real number set, so that means it can't be periodic, right? Next graph is of cos inverse x. Similar to the sine inverse x, cos inverse x has its domain as absolute value of x less than equal to 1, and its range is from 0 to pi. 0 as well as pi is included, right? So in sine inverse x, you can see the height of the graph. Height of the graph was minus pi by 2 to plus pi by 2. You have graph height as pi. Complete height would be pi, right? We are just saying the graph height of the graph. There might also be some question related to it. That's why I am writing it over here. The height of the graph is basically this much, that is pi. Here also you will get the height of the graph is pi. This complete height is pi. Next, let us see some highlights related to cos inverse x function. So the first highlight we have is cos inverse x is bounded in between 0 to pi, right? If its range is from 0 to pi, you will have only and only points in this much range only which has some pre-image. No value more than pi or no value less than 0 will have its pre-image, right? Next is cos inverse x is neither odd nor even, because you can see that neither it is symmetric about origin nor it is symmetric about y-axis, so it is neither odd nor even. Next is cos inverse x is decreasing function in its domain. If you just see it in the domain, if you just only work in the domain, then you can comment all these things which are written over here. If you're not working in the domain, even the inverse function is not defined, right? So cos inverse x is decreasing function in its domain, which you can even see from the graph. As x is increasing, your value for y is decreasing, right? You are coming down, down and down, right? So that means it is a decreasing function graph. Even you can say that it is strictly decreasing, because at no point, there are no any two points which are having the same values, right? Even as the inverse exists, so the function must be bijective. That means it must be 1 1 and on 2 also. So no two points can have the same image, right? Next is maximum value of cos inverse x is pi, which occurs at -1. Earlier we were having the graph for sine inverse x. In sine inverse x we have an increasing kind of function. For an increasing function, you have the maximum value at the rightmost point. Okay, even if you can't plot the graph now, you can see that what value you are having at the rightmost point. Rightmost point is x is equals to 1 for increasing graph, right? So for increasing graph, you have rightmost point as the maximum. For decreasing graph, you have the leftmost point as the maximum. So here leftmost point was x is equals to -1. So you are having your maximum value for this particular graph as cos inverse x is equals to pi, right? Next is minimum value. If we are having the maximum value at leftmost point, so minimum value will be at rightmost point for a decreasing graph, right? So you have x is equals to 1 for at which the minimum value occurs, and it is equals to 0. It lies on the x-axis, right? Next is cos inverse x is again not a periodic function. You can even see from this graph that this is not a periodic function because it is not repeating itself, right? So this is not a periodic function. Any confusion in these two graphs till now? We will discuss all rest 4 graphs if there is no confusion in these two. Just quickly let me know if there is any confusion in these two graphs for sine inverse and cos inverse. Okay, we will discuss the next graph then. We have graph for tan inverse x. This is the graph of tan inverse x. This graph of tan inverse x is somewhat a kind of a mirror image of the graph of tan x. If you draw the line y equal to x, this is a mirror image in line y equal to x, somewhat like that, okay? So you can even remember it same. So it reaches up till infinity, like at x is equals to infinity, it touches pi by 2, right? So a kind of asymptote, you can say. This where the lines which touch the graph at infinity, those are known as asymptotes, right? So you can see that these two lines, these two lines which are dotted one over here, these two lines touches the graph at infinity, either minus infinity or plus infinity. No need to worry that at which point, like you can take even the plus infinity or minus infinity. Such lines which touches the graph at plus infinity or minus infinity are known as asymptotes of the graph. Here y equals to pi by 2 and y equals to minus pi by 2 are asymptotes for the graph. Next, let's just discuss what are the highlights for this particular graph first. So the first one is tan inverse x is bounded by minus pi by 2 to plus pi by 2. You can only have the pre-image for the points which lie in the interval minus pi by 2 to plus pi by 2, which is the range for this particular function, right? You will have the graph of all the inverse trigonometric function bounded, right? Bounded in between the intervals which are given as the range. So it is most important to remember the table which we discussed in second slide, what exactly is the domain and what is the range, right? Next is tan inverse x is an odd function. You can see that this graph is symmetric about the origin, and if the graph is symmetric about origin, that means it is an odd function, right? Next is tan inverse x is increasing function in its domain. You can see that as x value for x is increasing as you move towards this side, right? If you move from like here, I have drawn from -10 to +10 only. So basically if you are moving from -infinity to +infinity, so you can see x is increasing in this direction. That means you can see that if you move from this to this, that means your value for y in this direction is increasing and increasing, basically strictly increasing. That means your overall function has increasing function graph, right? If so ever there is a a breakage in the graph where you get the value as, like suppose you were having a graph like this function is not said to be increasing, right? Only if you have a complete increasing complete on its complete domain, you are getting the value to be increasing, only then you can say that the graph is increasing, right? Next is tan inverse x is an aperiodic function. Again, you can see from the graph that it is not repeating itself, right? As the graph is not repeating itself, so it can't be periodic. Even if you have the domain of the function as complete R, it is not necessary that you will have a periodic function. You need to remember this thing. If you have periodic function, then it implies that the domain will be a complete real number set. But if the domain is complete real number line, it does not imply backwards that the function is periodic, right? It is just a one-way result, right? Next is scot inverse x. Here's the graph for cot inverse x and some highlights. So graph for cot inverse x is, again you can see here, again you have the height as pi, right? In the previous one also you can see that the height of the graph was pi. Graphs which we have covered till now, all four graphs were having the height as pi. You need to remember this, okay? Next, here highlights are, first one, cot inverse x is bounded by 0 to pi. You will have the pre-image of all the points lying in between 0 to pi, right? And no point more than pi or less than 0 will have its pre-image. Next is cot inverse x is neither odd nor an even function. This is neither symmetric about origin nor it is symmetric about y-axis, so it will not be an odd function, even it will not be an even function, right? Cot inverse x is decreasing function in its domain. You can see that as value for x increases, value for y is decreasing. You can see that it is coming downwards. That means if you are increasing the value of x, the value for y is decreasing. So it's a decreasing graph. Next, cot inverse x is again not a periodic function, right? Even again you can see, even after having a complete R as your domain, you are not having a periodic function. Again, you can recall this to your mind that it is just a one-way result, that if you have a periodic function, you have your domain as complete R, not the other way. Next is cosecant inverse x. Here you have the graph and some highlights related to it. Cosecant inverse x, domain for this is absolute value of x is greater than equal to 1, right? Again, and you have y belongs to -pi/2 to +pi/2, but 0 is not included. You can even write it like this, or you can write like -pi/2 to +pi/2, sorry, +pi/2, cancelling the 0 from this, remove the 0. All right, so you have some highlights related to this are cosecant inverse x is again bounded in between -pi/2 to +pi/2. You will have only the values of cosecant inverse x lying in -pi/2 to +pi/2. Next is cosecant inverse x is an odd function. You can see that it is symmetric about origin. If you move like here you have a point on the positive side of origin, like here you have this much na, so you will have again a point on this direction, right? That implies that it is symmetric about origin. You can see that this point, then it has an image around this. That means it is symmetric about origin. Okay. Maximum value of cosecant inverse x is equals to pi by 2. You can see this from the graph that it has the maximum value at this point, right? And this point is basically at x is equals to 1. Here you have the value for x as 1. That means at x is equals to 1, cosecant inverse x will have its maximum attained value, that is pi by 2. Okay, next is minimum value for the same graph you have at this particular point. This minimum value is attained when you have value for x as -1, right? So at x is equals to -1, you have minimum value of the graph as minus pi by 2, right? Next is cosecant inverse x is neither increasing nor decreasing function. Most of the students get confused in this thing and they say that the graph is like basically decreasing, but it is not. Why not? Because at this particular point you are having the value as minus pi by 2, but next to this you have a point over here which is which gives the value pi by 2. That means there is some particular time at which, like at this, after this point, you have an increase in the value of the graph, an increase with the value in the graph, and increase was of pi value. So if so ever there is an increase in the graph only at one particular point also, you will say that the graph is neither increasing nor decreasing. Otherwise, if we just exclude this much portion, or we just say that in this particular portion it is decreasing, in this particular portion, even in this particular portion it is decreasing. But if we include, like say about the domain, we are basically working on the complete domain. So if we work on the complete domain, then we can't say that it is decreasing in the complete domain. Okay. Similar to this, we have secant inverse, right? This is the graph of secant inverse x. Here are the pointers related to it. You can even see that the range can be written like this, or you can write it as 0 to pi, where you need not to include, like pi by 2 will not be included. Again, you have boundedness for this graph by, it is bounded in between 0 to pi. And secant inverse x is neither odd nor an even function, because it is neither symmetric about origin, here's the origin, and nor it is symmetric about y-axis, right? So it is neither odd nor an even function. Minimum value, maximum value is at pi, like maximum value is pi, and this occurs at x is equals to -1. This is the maximum value which is at -1, and this is the minimum value which is at +1. You can even see that this graph is always greater than equal to 0. Such conditions are also used while solving questions, like basically the graph of cos inverse x, now secant inverse x you can see, or cot inverse x. These three graphs are always above the x-axis. So this thing can also be used in the question solving, right? So you need to visualize all such graphs properly, right? Next is secant inverse x is neither increasing nor decreasing. If you see in two separate intervals, in this much interval it is increasing. I agree that it is increasing in this much interval from -infinity to -1. Again from 1 to infinity it is increasing. But in the complete domain you can't say that it is increasing, because here you have a fall in the graph, right? A fall of pi value. Next, secant inverse x again is not a periodic function. So we have discussed the main highlights of all the graphs, and we have seen how to plot all the graphs. You need to visualize each graph very carefully so that you can answer the questions related to graph very easily. So do remember how to plot the graph or what exactly is the graph of each function. Any confusion till now? You can ask me. If you have any confusion till now in any of the function, you can ask, or we will proceed further. Okay, so I think that there is not any doubt. That's why you are not asking. Okay, so here is a problem for you, basically a question for you. So the range and domain of this particular function, you have f of x is equals to tan inverse of log with base 4 by 5, and input value is 5x square minus 8x plus 4. You need to find the domain and range. Okay, Bhuvan, no doubt. That's great. So if you have no doubt, let's just solve this question. You need to find the domain and range. Let's just see how we can find. How can we find the domain and range? Try this question. Quickly try. For domain, we need to see that what constraints do we have for writing the value of x, right? For tan inverse x, you have the domain as complete R, right? So if you, so ever you are getting the value inside this, like tan inverse, this much function is supplied to tan inverse. So this can take any real value so that tan inverse x is defined. So that means any real value over here will be there, so that tan inverse x is defined. So there is no constraint yet. Next, see, for log of 5x square minus 8x plus 4, for this value to be defined, we need to see that this much expression must be, this much must be positive, right? This must be positive. That means 5x square minus 8x plus 4. This must be positive so that log of this expression is defined. Now here you are having this, but this constraint is the only thing we have for constraint on our domain, right? So let's just see. According to this inequality, our domain will be decided. We have no other constraint for our domain. So domain will be decided with this particular inequality. The inequality over here is on some quadratic expression, right? So for a quadratic expression, if you plot the graph of a quadratic function, so it is a parabola, either an upward parabola or a downward parabola, right? And upward parabola is when you have the coefficient of x square as positive, and downward parabola if you have coefficient of x square as negative. Here you can see that the coefficient of x square is positive. This is positive. This implies you will have an upward parabola. You have an upward parabola. So this much thing is fixed that you will have an upward parabola, definitely. So if you have an upward parabola, and the constraint over here is that this upward parabola must be always giving the value as positive value. So if its value is always positive, that means graph must be somewhat like this. It must not, because if the graph is like this, or if it touches the x-axis, these are the three cases which we can have. If the graph is like this, then it is also attaining the negative values. That means this graph is rejected. If it is like this, it is taking the value like over here as like it takes the value 0 at this particular point. So if when this graph is rejected, so you have only this particular graph as your case over here. right? So let us just remove the other cases. We don't have other cases right now to be considered, so we will consider only this case when the parabola lies only above the x-axis. Above the x-axis, it can lie in the first quadrant or in the fourth quadrant or in the both. We don't need to take care of that, right? So if it lies above the x-axis and it neither cuts nor it touches the x-axis, that means the discriminant of the of the expression must be negative. Let's just see that whether the discriminant is negative or not, only then we can have this particular case, because this is the necessary thing for which the function must be defined. Let's just take discriminant over here would be minus 8 square of this b square minus of 4 a and c. So this would be 8 into 8, 64, minus 5 into 4, 20 into 4, 80. This is equals to minus 16, which is always negative. So discriminant satisfies our condition. That means we were according to this condition, we need this condition so that the function must be defined, right? So for given condition, a graph must be like this, and for the graph to be like this, our discriminant must be negative. All the conditions are satisfying. That means at no point you are having any such at no value of x you are there is no value of x at which this particular function is not defined. So that means the domain is complete real number set, right? So there is no particular value of x where the function is not defined. That means there is no value which has to be cut out from this complete real number set. You have complete real number set as your domain. Now come to the range. We have calculated the domain. Now come to the range. For range, how we can proceed? Let's just see. For that, you need to see that you are having your base value as 4 by 5. If you have base value of log as less than 1, then graph is somewhat like this, where it cuts at the point 1, 0. Basically, you have a decreasing graph. You need to just remember you have a decreasing graph. If you have the base value to be less than 1, if it is greater, if it would have been greater than 1, then definitely you would be having the increasing graph. But right now you are having the value of base as less than 1. That means you are having a decreasing graph. Now as you are having a decreasing graph, so you need to check for this input value, what is its minimum value and what is its maximum value. That will give basically the minimum and maximum value of this function which is inside the tan inverse x. I'll just erase some of the things which are creating mess over here, right? Okay. So basically the minimum and maximum value of this much portion log of 5x square minus 8x plus 4 will be decided accordingly if we check what is the minimum and maximum value of this quadratic expression, right? Because we know that we have monotonically decreasing graph. So at one end you will be getting maximum value, and at one end you will be getting at another end you will be getting the minimum value. So let's just check for that value. We have 5x square minus 8x plus 4. So this can be rewritten as 5 into x square minus 8 by 5 into x plus of 4, which can be rewritten as 5 x square minus 2 into 4 by 5 of x, right, plus of 16 by 5 and 16 by 25 minus of 16 by 5 plus 4, right? We are completing the square, that's it, right? So you can write this value to be equal to 5 into, this would be x minus 4 by 5 square of this, plus here you would be having 4 by 5 value, right? So this complete value inside value is basically x 5 into x minus 4 by 5 square of this plus 4 by 5, right? This is your expression. So if you are having the decreasing graph, that means maximum will occur at the leftmost point. You can see that if you have the leftmost point like this, if you have this much domain, then at the leftmost point you will be having the maximum value, and at the rightmost point you will be having the least value. So that means maximum will occur at which point? Maximum will occur at which point? Can you tell me? Anyone? Maximum will occur when this much portion is 0, right? So that you have a minimum value of this complete function, right? So its maximum will occur at 4 by 5, or you can say its maximum value is, and its maximum value is 4 by 5, right? Its maximum value would be 4 by 5 because this much portion will be 0 and this would be 4 by 5. And its minimum value will be like here, if you put the value of x, definitely this value will increase and it will reach till infinity, right? And here if you put the value of x to be infinity, you can see the graph is decreasing, right? So that means basically the minimum most value you will have is minus infinity, right, where it will end, right, at minus infinity. So this value belongs in between minus infinity, this value is in between minus infinity till 4, right? From minus infinity till 4 you have this value. Now you just need to see that for tan inverse x, if you supply the value of to the tan inverse x as log of 4 by 5 of minus infinity to 4 by 5, you need to see that what would be the range. This is your task. Now you can see this easily. Basically log of minus infinity to 4 by 5, these much values are given to tan inverse, right? So you are having for this much value, you can see that what would be the value of tan inverse. This is your work, you can do this now. Okay, Ayush, you are late, not an issue. You can now see that what values you can take for this particular graph, right? Next question for you is this: equation of the image of the line x plus y equals to sine inverse a raised to power 6 plus 1 plus cos inverse a raised to power 4 plus 1 minus tan inverse a square plus 1, where a belongs to R, is given by. Okay, you are a new student. Welcome to the session. So you can start from here. Basically, we are discussing a new chapter only today, which is inverse trigonometric function. So here we have, till now we have just discussed the graphs related to inverse trigonometric functions, and based on that we are solving few questions. So here's the second question we are having. Equation of the image of the line. Basically this is the given line. You need to solve this first and then you need to check what will be its image, right? Equation of the image in x-axis basically you need to see, right? So image should be taken. For that you need to solve this equation first. So let's just solve first. Here we have an equation like this: x plus y equals to this, right? We can see that sine inverse of a raised to power 6 plus 1, cos inverse of a raised to power 4 plus 1 minus tan inverse of a square plus 1. we have the domain of sine inverse, cos inverse and tan inverse individually with us. Domain for tan inverse is complete R, right? I'll write this as domain only, otherwise you will confuse yourself with like x over here. So okay, so domain is complete R. I'll just rewrite domain. I'm writing over here. Its domain is absolute value of x is less than equal to 1, and for this you have the domain same as this, absolute value of this is less than equal to 1, and here you have domain as complete R. That means a raised to power 6 plus 1 must be less than equal to 1. Again, a raised to power 4 plus 1 must be less than equal to 1, and a square plus 1 can take any real value, and all the values must be satisfied so that the line can be like constructed. That means you can see from the first and second one, a raised to power 6 and a raised to power 4 is always greater than equal to 0 when a belongs to R, and this thing is already given to us that a belongs to R. That means if you take a raised to power 6 and a raised to power 4, any other value greater than 0. I started this session at 4. So basically 50 minutes for this session are already over. So right, yeah, I started at 4. So a raised to power 6 and a raised to power 4 will always be greater than equal to 0, right? So that means this value is always greater than equal to 0. Now if you put any other value rather than 0, definitely this value inside this like absolute value of a raised to power 6 plus 1 will be greater than 1, but we want this value to be less than equal to 1. For that we need to have a raised to power 6 equals to a raised to power 4, which is equals to 0, which implies a must be 0. Now using the domain we have the value of a, but if you don't have the like what exactly is the interval for domain, then you can't just solve this question. For that you need to remember the domain and range. Okay, so a is equals to 0 so that this line can be constructed or it can be defined. That means you have the value over here as x plus y. X plus y is equals to sine inverse of 0 plus 1, sine inverse of 1 plus cos inverse of 0 raised to power 4 plus 1, that is again 1, minus tan inverse of 1. Just put the value of each. Sine inverse of 1 is same as pi by 2. Here cos inverse of 1 0 minus tan inverse of 1 you have pi by 4. So you have overall value as pi by 4. Now if you want the image for the same in x-axis, image in x-axis you want, that means you just need to shift y to minus of y, you need to replace y with minus y and you have the same line. That means you have x minus y equals to pi by 4 as your line. Okay, so from tomorrow you can join from tomorrow, or you can see this session when it is over, right? Next question, or you can say next properties. Basically we will be discussing the properties now, which is our second section and the most important section. I won't be discussing like how we will be deriving all this, because this will unnecessarily increase the length of the basically increase the time of this session. I'll be discussing the memory tips, like how you can remember all those properties, because there are so many properties in this particular chapter only. So we will be discussing some of the memory tips for like most of the properties we have, so that you can remember them. Okay, yeah, Mario, hi. Hello, welcome to the session. So here we have set of properties for the first one. So first properties are based on such functions where you have some trigonometric function over its inverse function, like sine of sine inverse x, cos of cos inverse x, tan of tan inverse x, cot of cot inverse x, cosecant of cosecant inverse x, and secant of secant inverse x. Now, you need to remember, like, mostly f inverse x is equals to x, but for this condition to be satisfied, this value which you are inputting over here must lie in the domain of f inverse x, right? You remember this basic property, and if you remember this basic property, you can remember these 6 properties very easily. How? Let's just see. Yeah, I know somewhat of Hindi, but most of the students are here from all the regions, so if I speak in Hindi, they won't be able to understand. Okay, so sine of sine inverse x is basically x. If the domain of, like, whatever values of x you are providing over here now, that must be lying in the domain of this sine inverse x function. So if you have this x value lying in the domain of sine inverse x, that means you will have the value of sine inverse x as x only. You can see this is happening in all the functions. You have cos of cos inverse x is equals to x only when x lies in the domain of cos inverse x. Again, domain of tan inverse x was x belongs to R, so here you have x belongs to R. Similar is the case for cot inverse x. And for cosecant and secant inverse x, you are having the domain as absolute value of x is greater than equal to 1, right? You can see both of them have the domain as absolute value of x is greater than equal to 1. So if you put the value of x lying in this domain, then cosecant of cosecant inverse x will be x, and secant of secant inverse x will also be x. Also, you can see from this that these two functions are identical. These two functions are identical, and these two functions are identical. And as the functions are identical, that means their graph will be same. So graph of both the first two, like I am marking them as first and second and marking them as third. So this is the graph of first, this is the graph of second, this one is the graph for third. Or first two have same graph, next two have this graph, and next last two will have this graph. How? Basically, this is defined when x is either less than 1 or greater than 1. So either less than 1 or greater than 1, you can say. Next, these two, tan and cot, are defined for all the values of x. That means this line is basically touching till infinity. You can extend on both the sides. And for sine and cos, you have a restricted domain in between -1 to 1. That means you will have a line segment, right? Basically, here you have a line segment, here you have a line, here you have two rays. You can remember like this also, line segment, line, and two rays. Okay, thanks Ayush. Okay, next is property 2. Here we have our property 2. In the previous one, we were having sine of sine inverse x. In this one, we have sine inverse of sine x, right? Now, how will you remember what x values has to be supplied over here so that you get value of the function again as x? For that, you need to remember the earlier one was over here was sine of sine inverse x. The value of x was first solved for with sine inverse. You first took the sine inverse, then for that value sine has been taken. Now, but in this one, what is the main task? Whatever value you supply over here for x, right? You will take sine first, sine of that value first, then you will take sine inverse of that value. Now, so that the function must be satisfied now. This value of sine x must lie in the domain of sine inverse. If this value has to be, this value needs to be lie in the domain of sine inverse, that means this value of x must lie in the range of sine inverse. Like first you will take shift from range to domain, and then again from domain to range. That means you will get the range back. Range to domain, here you supply some range, you will get the domain, again you will getting the range. That means only in this case you will be getting the x value back. That means in this one you will remember that x here must lie in the range of inverse trigonometric function of each. Like for the first one, right, here you have for the first one sine inverse of sine x, right? So for the value for sine inverse sine x to be same as x, what you need, the x value must lie in the range of sine inverse x, and the range of sine inverse x is minus pi by 2 to pi by 2, which we have already discussed, right? So its value for x over here is pi minus pi by 2 to plus pi by 2. Next, similar for the cos inverse of cos x, again cos inverse of cos x, here x would be same as the range we have for cos inverse x. Range of cos inverse x is same as 0 to pi, right? Range of cos inverse x, you all know that x will belong to, like range of cos inverse x would be y belong to 0 to pi, so you need to supply this value only, 0 to pi. Similar is the case for tan inverse of tan x, you have its like range for tan inverse x is minus pi by 2 to plus pi by 2, open interval means pi minus pi by 2 and plus pi by 2 will not be included, right? So you have values from minus pi by 2 to plus pi by 2. Next is cot inverse of cot x, that is from 0 to pi you have, okay, my name is Ashwita. Okay, next you have cot inverse of cot x. Again, here you need to see what is the range for cot inverse x. You have earlier started, that is from 0 to pi, open interval. So 0 to pi we have all the values, but 0 and pi are not included. Again, you can see the range for cosecant inverse and secant inverse, same as this value written over here. This is the way how you can remember. In the earlier one, you need to see the domain of inverse trigonometric function. Here you need to see the range of inverse trigonometric function. Okay. Next property, like in this one, basically, see this slide. Basically, we have the values of x, some predefined, only then we will get value of x back, right? But what if we provide some other value for x? In that case, sine, cos, tan, cot, cosecant and secant all will be defined, but taking the inverse of it won't be same as x. So what that value will be, if you need to calculate that value, for that you need to know the graph of each of these functions. Sine inverse of sine x, cos inverse of cos x. Let's just draw and see what like how you can depict from the graph. Here's the first graph. You have sine inverse of sine x. As discussed, like as this value minus pi by 2 to plus pi by 2. This much value is in the range of inverse trigonometric function of sine inverse x. So you will have the value as y equal to x, so always, right? You will get the value back. But for other values, if you supply some other values either greater than pi by 2 or lesser than minus pi by 2, then what value you will have for this particular function, if you have this function, right? Let's just see. Its graph is basically something like waves. Like you can remember it as sine x, some graph, sine x has some graph like this now. Just sharpen this graph. You will have the graph of this sine inverse of sine x. Basically just sharpen this graph and you can remember this graph very easily, right? This much is y equal to x, and at pi by 2 it decreases, pi by 2 to 3 pi by 2 it decreases, again at 3 pi by 2 to 5 pi by 2 it increasing, just at like it is basically a periodic function, it is increasing, decreasing, increasing and decreasing. Okay, so how these graphs are basically helpful for you to calculate the value for a given x. Let's just see that. For that you need to calculate this value first. If you have sine inverse of sine of 1, this you need to calculate. So how can you calculate? Basically you can see that 1, this value 1, you know pi by 2 is somewhat around 1.57, somewhat approximate 1.57 you have. So one value will lie left to the pi by 2 and right to the 1. So that means it will lie somewhat over here. If you draw a perpendicular to the graph, that means you are touching y equal to x line. That means whatever value you are having over here as the like result for sine inverse sine x, that is same as whatever value you supply over here. This value which you supply over here is x, and value you are getting is y. So y here is according to this line, you are touching this line now, so you are getting x value only. That means you are having one value back. Even you can answer this directly. How? As 1 lies in between minus pi by 2 to plus pi by 2, which is in the range of sine inverse x, that means it will have its value back, right? But what if you have to calculate sine inverse of sine 5 or sine inverse of sine 10? Such values you need to calculate. So sine inverse of sine 5, let's just see. We have this 3 pi by 2, and 3 pi by 2 is somewhat around 4.71. I'm just approximating the value, and this 2 pi is somewhat 6.28. That means 5 will lie in between these 2 points, and for this line we are having this particular line which is y equal to x minus 2 pi. That means x over here we are having as 5, so that means it will have the value 5 minus 2 pi as the answer. This is how you use these graphs so that you can calculate these values easily, right? If you like sit and then calculate for sine inverse of sine x applying all the properties, definitely you will have some mistakes. But if you remember this graph, like it has a graph somewhat like sine x, but just you need to sharpen this up, then you can easily like find the values of such functions at each point. Okay, next is the graph for sine, like here we have sine inverse of sine x. Next is for cos inverse of cos x. Here we have cos inverse of cos x like this. Again this graph is somewhat like sine inverse of sine x, but what here we have done is we have just shifted this upwards. Just shift this graph up till the x-axis, making it always positive. It is same as sine inverse of sine x, just shift it upwards until like you have to shift it somewhat towards the right also, right? So you have this graph of cos inverse of cos x. You need to see that here the height of the graph is also like also matters in all such graphs also. So pi by 2 till positive pi by 2, and downwards we are having till minus pi by 2. Again we have height as pi. Height is pi. In this one you can also see from 0 to pi you are ranging. That means height is again pi. Okay. Okay, so Ayush, you can see the yourself if you can understand from the between of the session. Like it must not matter to the students that how many students are like watching this session, I hope. Okay, so yeah, okay, so let's just begin. So cos inverse of cos x, you have these lines with you. You can or like write the equation of each line very easily, just like using the slope intercept form, y equal to mx plus c. If you know, like using this you can write the equation of each line very easily. Okay, this is the graph for cos inverse of cos x. Next we have the graph of tan inverse of tan x. Here's the graph of tan inverse of tan x. This you can remember, which is similar to tan x graph. Like in tan x you had something like this, na? Again, as you have sharpened in the case of sin x graph, here sharpen in case of tan x graph, you will get these lines. This is how you can remember, right? For sine inverse of sin x, you recalled for the graph of sin x and then you sharpened it. For cos inverse of cos x, what you did, you shifted it upwards, seeing the graph of sine inverse of sin x. For tan inverse of tan x, you recalled the graph of tan x and then you just tried to sharpen it and you were easily able to recall. Okay, no need to be sorry, that's it. Like you can just learn over here, come and learn over here, that's it. Okay, and if you need to learn more, you can always and always welcome to download our practically application. There we have run the full-fledged courses. Even you can ask the doubts, like interact with all the teachers over here. Next graph over here is cot inverse of cot x, right? So cot inverse of cot x here is similar to the tan inverse of tan x, but this time what you did is similar to cos inverse of cos x. What you did is shifted it upwards. Just shift the graph of tan inverse tan x upwards, that is above the x-axis only. You will get a similar case for cot inverse of cot x. Okay, you have already downloaded, that's great. So I hope you are enjoying those 3D model videos over there. Most of the students have a better edge over there after learning the concepts from 3D videos. Next, here's the graph of cosecant inverse of cosecant x, and we have the graph of secant inverse of secant x. So these are similar to sine inverse of sine x and cos inverse of cos x, but the values like this, which are not there in the domain of this function, are excluded. These are similar to sine inverse of sine x and cos inverse of cos x, but the values which are not there in the domain, so that must be excluded. That's it. Okay. Next property third we have over here. This property is quite easier to remember. How quite easier to remember? If you know, like you have already know from like trigonometric function, which you have already done in like also the in grade 10th, you are already doing this trigonometric function. You know, sine of theta equals to 1 by cosecant theta, or you can write it in reverse, like cosecant of theta equals to 1 by sine theta, or you can say cos theta equals to 1 by secant theta, or you can write even the reverse of it. And similar you can write for tan theta equals to 1 by cot theta. Using these properties, you can easily write all these and like one another. But how will you write the basically the constraints over x, right? How will you write? If you are supplying the x value to cosecant inverse x, that means x value must be according to cosecant inverse x, and cosecant inverse x has its domain as absolute value of x as greater than equal to 1. That means you have constraint as absolute value of x greater than equal to 1. Next, again here you have sine inverse of x equals to cosecant inverse of 1 by x. This is already know, using these relations we can easily write. But how we will write this domain? Let's just see. This time x is supplied to sine inverse x, right? X is supplied to sine inverse x. If x is supplied to sine inverse x, so x must be according to sine inverse x. So if x is according to sine inverse x, that must be absolute value of x is less than equal to 1, which is the domain of sine inverse x, right? So you have the domain of sine inverse x as absolute value of x is less than equal to 1. But if you supply the value of x as 0, then 1 by 0 for cos inverse x will be 0, which is not there in the domain of cosecant inverse x. So that means x is equals to 0 has to be excluded. Similar cases you can do for secant, cos and cot, right? How can you remember cot? Like if you have tan inverse of x, if you input the value of x as positive, here you will have 1 by x. I'm sorry, it would be 1 by x. If you have x as positive, then you have tan inverse of 1 by x as cot inverse x. But if you have x on the negative, x like you have x like on the negative side, then you need to add pi to it, right? Next set of properties are this property 4, you can say. This is basically if you supply, okay, hi Koshi Bhardwaj, hello, welcome to the session. So this set of properties, what are these basically? Let's just see. If you supply minus of x to all the inverse trigonometric function, then how do they behave? Let's just see that. I'm good. How are you? Hello. So let's just see the properties. Sine inverse of minus x is equals to minus sine inverse x. Basically, how you can remember this, let's just see. Here you can see all the constraints on x basically are from domain of inverse trigonometric function. Constraints on x are based on the domain of inverse trigonometric function, right? And after like setting the constraints, how you can remember this property is sine inverse of minus x. For sine inverse x, tan inverse x and cosecant inverse x, I like said you earlier that remember these like two sets of triad, basically these three functions together and these three together, right? Like what basically is done for sine, tan and cosecant, minus sign jumps out of the function. You can remember this directly. For sine inverse, tan inverse and cosecant inverse, minus sign jumps out of the function directly. You can remember this. And in case of cos inverse, cot inverse and cosecant inverse, what exactly is done is minus sign jumps out, that's sure in all the cases, but in these three cases you need to add pi for in all these three cases. Pi minus cos inverse x, pi minus cot inverse x, pi minus secant inverse x. This is how you can remember. Remember sine, tan and cosecant together, and remember cos, cot and secant together, right? In case of sine, tan, cosecant, minus sign directly jumps out of the function, and cos, cot and cosecant just add pi to all the functions, okay? Right now inverse trigonometric function is going on, Koshi, right? So like already the most of the parts of this chapter are done. In the next session we will be covering the previous year questions of this particular chapter. Till then I hope from each one of you to cover this chapter. I tried my best to give you the memory tips of each and every property over here so that you can remember. In this particular chapter, the difficult task which students has to do is to remember each and every property. That's it. Mostly students get nervous, like they feel tense that how can they recall so many properties. So I tried to give you the best possible memory tip over here. So do see the complete session properly and remember each and every property till the next session so that you can solve questions with me, right? Here are few more properties. Property 5 we have as sine inverse x plus cos inverse x as pi by 2, again tan inverse x plus cot inverse x as pi by 2, and cosecant inverse x plus secant inverse x as pi by 2. How you can remember this? Function plus cofunction gives pi by 2, and constraint on x is same as domain of function. Just remember this, and like basically you can write all these three properly. How? Let's just see. Function and its co-function. Let's just say sine inverse x is a function, so its co-function sine cosine, right? So its co-function is cosine. So sine inverse x has its co-function as cosine inverse x, right? So adding both, you will get pi by 2. And what exactly is the constraint on x? You have constraint on x as x varies from -1 to 1, right? Next is tan inverse x plus cot inverse x. This will sum up to give pi by 2. And so here you again see tangent and cotangent, co-function of tangent, right? So adding these two, you will get pi by 2. And this value for x ranges from minus infinity to plus infinity, which is same as domain of function, right? Next is cosecant inverse x plus secant inverse x. Secant x, its co-function as cosecant function, right? So these two add up to give you pi by 2. Again here the value for x ranges from minus infinity to -1 and then 1 to infinity, right? So you have this as same as the domain of function. Okay, here's a question for you to solve. Let's just solve this together based on the properties which we have just done. Find the value of x belongs to -1 to 1. We are already given that x will belong to -1 to 1. So based on this thing, we can see what are the properties which we can apply over here, right? So 4 sine inverse x plus cos inverse x is 3 pi by 4. This is the equation which is given to us. 4 times sine inverse x plus cos inverse x is equals to 3 pi by 4. You can see the previous slide. In this we have sine inverse x plus cos inverse x equals to pi by 2 if x lies in between -1 to 1. And we already know in this particular question x lies in between -1 to 1. This is given to us. That means we can use that property. If sine inverse x plus cos inverse x is equals to pi by 2, this is what we know. That means cos inverse x is equals to pi by 2 minus sine inverse x, because we have the constraint over x already with us. That means 4 sine inverse x plus cos inverse x is pi by 2 minus of sine inverse x, which is same as 3 pi by 4. Just solve it for sine inverse x. For sine inverse x minus sine inverse x, you will have 3 sine inverse x, right? So you have 3 sine inverse x, which is same as 3 pi by 4 minus of pi by 2, which is pi by 4. That means sine inverse x is equals to pi by, taking this 3 to the other side, you have pi by 12. So this implies x is equals to sine of pi by 12. Pi by 12 is 15 degrees. So I already told you to remember the value of sine 15, sine 75, cos 15, cos 75. They are like used more oftenly in all the examinations. So this value of x will be under root 3 minus 1 by 2 root 2. This is the required value. Okay. Next set of properties is this one. If you add tan inverse x to tan inverse y, then how can you write the property? Let's just see the numerator. You can remember the second one very easily because here is just one case. This is basically like derived, and you can even remember this on the basis like tan of a minus b is equals to tan a minus tan b over 1 plus tan a tan b. right? Based on this property, even this property can be derived, or you can relate both the properties to remember them, right? Like if you have tan inverse x and tan inverse y, subtraction, here you have subtraction, here you have tan a minus tan b, like here you have subtraction over here and addition in over here, and 1 added to the tan 1 plus tan a tan b, so 1 plus x into y. Similar, there are, these two are similar results, like even they are derived from this particular function. So you can just note this down in your mind, like how you can remember this. In case of subtraction, you just directly write this from here, okay? And in case of addition, how you will remember, let's just see. Okay, you are from UP, okay, I'm from Punjab. Okay, here tan inverse x plus tan inverse y. You have tan inverse of x plus y over 1 minus xy. If you have x into y as less than 1, x into y as less than 1. How you can remember this property? Let's just see. When you get plus sign, the first task you need to do is task 1. Task 1 which you need to do is check for x into y. If x into y is less than 1, directly use this property. And this property is similar to tan of a plus b is equals to tan a plus tan b over 1 minus tan a tan b, right? So if you use this property, like however you remembered this property now, this property, first one is similar to that. If you remember the formulas in trigonometry, you can directly remember the formulas in inverse trigonometry. They are parallel to each other, right? So tan of a plus b is similar to this one. So if you have the, just check for x into y. If x into y is less than 1, if x into y is less than 1, that means your denominator which is 1 minus xy is positive. So if denominator is positive, write the result as it is. That's it. How you need to remember, if x into y is less than 1, that means your denominator is positive, and if denominator is positive, write the result as it is. And if x into y, this is the first case and this is the second case, if x into y is positive, like x into y is greater than 1, in both the cases you have x into y as greater than 1, then you need to check the sign individually, sign for x and sign for y. If they have same sign, only then you can find the value further using these formulas. If they have different signs, then you can't find the value directly. So basically you have x is greater than 0 and y is greater than 0. That means you need to add pi to this function value, right? And if you have both the signs as negative, that means you will subtract pi from it. Okay. Here's a question for you. Let's just solve this question. Find the x satisfying the inequality cos inverse x is greater than cos inverse of x square. We are majorly done with all the properties we have in this particular chapter. There are few more properties which I am not covering it right now, and even according to my suggestion for mains, those are not required. If you remember, like if you want to remember more properties, you can definitely remember, but like the work can be done even with these much properties. Like if you have sine inverse x plus sine inverse y, sine inverse x minus sine inverse y, cos inverse x plus cos inverse y, cos inverse x minus cos inverse y, all such properties are there in your NCERTs or in your reference books which you like go for like solving for mains questions. But I suggest you don't remember these many properties, as work can be done easily if you remember just for tan inverse. This formula, if you remember, you can solve for sine inverse also by converting that sine inverse into tan inverse. Okay. So I suggest you to just remember this formula properly, and this much formula is enough so that you can solve the question related to sine inverse and cos inverse. Okay, let's just solve this question. We have cos inverse x is greater than cos inverse x square. If you remember the graph of cos inverse, I have already drawn this for you also. It is somewhat like this. This is pi by 2, this value over here is pi, right? And this value minus 1 or 1. Or even if you don't remember the graph, how you can solve, in that case you need to remember the highlight which I have given you for this particular graph, which was cos inverse x is a decreasing graph. In case of decreasing, what you must have is x must be less than x square, only then cos inverse x must be greater than cos inverse x square. That means x square minus x is greater than 0, right? In that case you have x into x minus 1 is greater than 0. So if you plot the way using the wavy curve method, you have 0 1. Using the wavy curve method, plus minus and plus you have. That means according to this inequality, you have x belongs to minus infinity to 0, union 1 to infinity you have, right? But cos inverse of x is defined only for minus 1 to 1. It is defined only for minus 1 to 1. So intersection of this complete has to be taken with minus 1 to 1, because out of the values which are less than minus 1 or greater than 1, at those particular points cos inverse is not defined, right? So that means this intersection has to be taken. That implies x will belong to minus 1 to 0. You have this as your answer, right? Next question is this one, which I am giving you as a homework, right? Do practice this question on your own, and if you are able to get the answer, let me know in the comment section. If you are not able to get the answer, even then you can let me know up till what point you have reached, right? I'll definitely discuss this in the next session. Okay, we will have tomorrow at this particular time you will be having chemistry session, and day after tomorrow you will be having mathematics session at the same timing, 4 to 5:30. That chemistry session is also for JEE, so those who are preparing for JEE must see that all the sessions at 4 to 5:30. So I thank you all for a good interaction over here, and I want a bit more interaction in the next session. For that, you can share this link with your friends so that they can also join from the next sessions, and you can set the reminder, like you turn on the notification button, that so that you have the notification for all the live sessions we have over here. And if you like the session, do share this as much as possible, and you can like and follow us on our social media platforms also. So till then, goodbye, take care. We'll meet you up in the next session.